So hi everybody, thank you so much for coming. I wanted to introduce Mike Duclos, who, at least in my humble opinion, is sort of like a legend of the passive house and deep energy retrofit world. So Mike gave a presentation at the Massachusetts Passive House monthly meeting. Yeah, and I just thought this was a really important topic for all of us to hear. So Mike is the founder and principal of DEAP Group. So they are a consulting firm that works in deep energy retrofits and high performance buildings in general. And Mike has like every certification. He's a HERS rater, and there's a million certifications that he has. I'm not going to list them all off, but he has a mechanical engineering background, right?
Actually, electrical.
Electrical.
Yeah.
Okay. Yeah. So I'm just going to hand it over to Mike, and if you have questions along the way, you said that you'd be willing to...
Yeah, if there's something you really feel like it's seriously wrong, and I'll stop at one point and just ask, because there's one principle I want to focus on, but something that really needs to be clarified by now, by all means raise your hand and we'll address it. It's just in the interest of keeping this to a bounded set of time. So with that, great. So Beverly, thanks very much for the introduction. I started out as an electrical engineer. I used to do integrated circuit design for communications companies in 495 belts. And I've worked on two bet the company designs. That is to say, if the company, if I had failed to deliver the product working on time the first time, the company would have failed. This sort of put me in an awkward position when I went to my next job, because one of the first questions people ask in interviews is, why are you no longer your former employer? So if I'm a detail-oriented person, I think what I'm trying to do is cover the details that are important, and we'll see what you think of that argument. I also believe in being end-to-end on a process. So starting out at the design phase, I'm a certified passive house consultant, have been since 2009. I've worked on certifications for both Passive House Institute and Passive House Institute US and successfully, and have a number of projects in process right now that I'm wrapping up. And with being at the design phase, going to the building and seeing how it is constructed, doing inspections, doing all the testing at the end, and then monitoring the results of the building, I feel is the best way to get a picture of exactly what's going on, and I can use all that information when I go back to the next design and start again. So the reality check is really important. I've been with the Mass Save program as a HERS rater in the new construction program since about 2009. Paul Drinkamp, who you may know, and I founded the Deep Energy Group. I have online training. For example, Passive House in the Real World is intended to be a taste of what it would be to become a Passive House consultant without investing in rather lengthy and expensive training. And the Real World is the reality check part of it. I worked on over a dozen deep energy retrofit programs, so I've got a profound sense of how very expensive they are and how we're not going to take that path with any large quantity of buildings. We were able to reduce energy use in these buildings 85% and document that with utility bills 5 years running, no problem. Very expensive to do. So I think if we're going to make energy reductions, we're going to have to be more clever than that. And what that really said to me is, every new house we built that is not good enough to be out there in 2050 is another liability we're going to have to deal with. 85% of the buildings that we're going to have around in 2050 are in the ground today. And every house that is 5% better, like the Mass Save program provides incentives for, in my opinion, is adding to that problem. So, I'm basing a bit of this presentation on what Rob Aldridge did at Passive House Institute US North American Conference in September in Boston. And we'll get to those. And I'm going to do an on-ramp here. So there are going to be a number of slides in the beginning that provide introductory concepts and language. So if people aren't very familiar with this, that's why I'm doing this. Someone let Jonathan in. Just at the door there. And as I mentioned, questions as we go, if they're important to understanding. And I'd like to express my sincere appreciation for the time, technical support, and insightful feedback I've received from Ryan Flynn of Mitsubishi. I showed him this presentation. He made a lot of very good suggestions. We worked on those together. And I think as a result, it's a much better situation. So we'll get started with that. To measure is to know. This is Lord Kelvin of the 0 degrees Kelvin fame. And he was very, identified very much with the idea that if we don't measure things, we have an imperfect knowledge at best. So measurement is a really good thing, and understanding that connection to reality is very important. So the context that I'm coming to you with this is the Supreme Judicial Court in Massachusetts ruled that Massachusetts failed to meet the requirements of the Global Marine Solutions Act in 2016, and so Mass is trying to adapt the 2030 Comprehensive Energy Plan, which is the mechanism by which compliance is going to be done. Should be coming out soon. It's for 2030, but not 2040 and 2050. I've got a bone to pick with that, because if we don't know what we need to do for 2050 and 2040, we may be making mistakes now that will survive that long and be a problem, like making buildings that aren't good enough. So Massachusetts has air source heat pump incentives, Mass Save, Mass CEC, alternative portfolio, and I understand the reasons for the existence of those programs to address the greenhouse gas impact of the heating houses in Massachusetts principally. That's my take on it. Mass Save is not chartered that way. That's the Energy Efficiency Advisory Council. They don't have any direct greenhouse gas reduction feedback. They're supposed to claim savings. That's what they do, and we'll talk a little bit about that later on. Don't want to get into that right now. So, question, do incentive programs assume published air source heat pump performance data are delivered in reality, including the accounting for greenhouse gas reductions for this target? That's a question I have. Does measured air source heat pump efficiency can be dramatically different from published data? And we're going to use Rob's summaries of 3 studies to address that. So that's where we're going with this. Probably you've seen this before, but this is from the Lawrence Livermore Berkeley National Lab. And this is how we make electricity and other things in the United States. So we have all these sources, solar, nuclear, hydro, and fossil fuels like natural gas, coal, and oil on the left. And then on the right, we have useful energy. And if we look at the electricity block, we put 3 times the amount of energy into the electricity block we get out of it. So we have a primary energy factor, or an efficiency of 1/3. The primary energy factor is 3 times as much going in as coming out. This has greenhouse gas implications. So if we're going to do the 2050 target, which maybe should be 2040, and maybe it should be 1.5 degrees C rather than 2 degrees C. If you've heard about the recent IPCC report, International Panel on Climate Change report in October, maybe we should be shifting the goalposts, but let's assume not for the moment. So we're going to talk about models here, models for heat pump performance, models for how programs work, models for how we perceive things. And George Boss is a famous statistician, and one of the things he did and is famous for, I think, is experimental design. How do you design experiments so they actually measure the things you expect them to measure and have that within a certain amount of tolerance? So this is something I make computer models for energy simulations, for certifications, and so forth. All my models are wrong, and all the information in this presentation is wrong. Is it close enough to be useful? That's the metric, okay? So I'm trying to provide reasonably close data here, and I'm making some simplifications so we can get through a lot of material in a short amount of time. So I'm an engineer. When I go to school, they say, look, do a black box analysis before you do anything. Look at the inputs, look at the outputs. So that's what we're doing for the air source heat pump. The air source heat pump block gets electricity in, and it gets heat from outside or delivers heat to outside. And we're just going to talk about the heating performance of air source heat pumps. Nothing to do about cooling. I'll mention that only in passing so that we can just assume everything's going one way. So heat is being taken from outside, and it's being delivered to inside a building. And if we put in 1 unit of electricity, we get out 3 units of heat moved. And this isn't defying the law of conservation of energy. We are moving heat, we are not creating it. Just like a electric water pump doesn't make water, it moves it. We're compressing heat, we're squeezing it together, we're raising its temperature so that it's useful to be inside the building. So the output energy divided by the input energy, what we get out is the coefficient of performance, and that's the really important number we're going to be talking about throughout this presentation. Here, we're getting 3 units effective what we want for 1 unit of energy expended, the coefficient of performance is 3. So electric resistance heating is 1. We're just turning electricity into heat. No mechanical and no advantage there, no coefficient of performance there. Now, in that box, some interesting things happen, and we can't believe a simplified model of this too much. So we're going to try to tease this apart a little bit and see a little bit of the spectrum, but not all of it, a comprehensible amount. So, what is the impact of coefficient of performance on CO2? So, if you Google pounds of CO2 per kilowatt hour, you'll get as a Google hit EIA, Energy and Information Agency. It's a sub-department, Department of Energy. They know everything about energy use in the United States, past, present, and future. That's their job. And what you get when you do this is they say, if you want to know the answer to this question, take the number of megawatt hours of electricity that are generated in the state, divide by the CO2 emissions. So they have these tables, you know, and you just add that all up, and I convert it to kilopounds, and then do the division, and I get about 0.8 pounds of CO2 per kilowatt. Anybody have any big argument with that? That's okay. So in the United States, it's above a pound on average, and there's a lot of coal out there. So that's the number. Now, if I take it natural gas that I could have generated electricity with, bring it to a house, and here's the number of pounds of CO2 in a million BTUs of natural gas. And if I convert that to kilowatt hours, it's about 0.4. So if I take that natural gas and burn it in a house with a fuel efficiency rating on the furnace of 95%, it costs me 0.42 pounds of CO2 to make a kilowatt hour of heat in the building. Is that clear? Any questions on that? So we've got an alternative. We can put the gas in an electric heating system. We can put the gas in a furnace. And that's what happens there. So because we're at a disadvantage when we generate electricity from natural gas because of that 3-to-1 coefficient of performance issue, we have to use the coefficient of performance to multiply that back. So what I've done is I've done some math on using the electricity CO2 for a coefficient of performance of 3, 2.5, 2, and 1.85, and these are the pounds of CO2 per delivered kilowatt hour of heat in the building. So we're comparing heat in the building to heat in the building. Why is that in red? Somebody raise their hand and take a guess. Why have I got that number in red? Yes, Jonathan.
It's equivalent to the gas illustration.
Yeah. So at 1.85, we're actually doing more harm than good because we're generating slightly more CO2 than we would if we put that in a furnace and burned it on site. That would be bad. Because the whole point of this, right? At the beginning I said we're trying to reduce greenhouse gas emissions. So if we're averaging 1.85, or I would argue even slightly higher, because it takes energy to make the heat pump and all that, we're doing more harm than good. On the other hand, if we can get the COP up here, so that's why I'm here today, to see if we can make that happen. See if we can push the delivered actual real COP as high as we can get, because that's going to reduce greenhouse gas emissions. That's why we're doing this. Any questions on that? That's pretty fundamental. Does that make sense? Okay. So, and that number is going to change when the pounds of CO2 per kilowatt hour go down as this renewable energy grid happens. If you want to see how likely that is to happen anytime soon and how difficult that is, David McClay, the physicist from UK, who does an excellent presentation on YouTube, and that is an interesting source, or just Google Saul Griffith for calculator. It's kind of a long, interesting thing. He's somebody from MIT who's done another very interesting analysis on how hard it will be to create an all-renewable energy grid. So, what's the coefficient of performance of the heat pump? That's an important question now. We need to answer it, right? So here's something from one of the studies we'll be touching on very briefly. We have on the vertical axis the daily COP, what's the average COP for the day, and the horizontal axis we have the temperature. So what's the air source heat pump COP? This is real data as opposed to two data points in a data sheet that say 47 degrees and 17 degrees. All right. So this is site 4, this machine is an FE18. So now let's go to site 1, and it's an FE18, same machine, right? So I'm going to go back and forth here. Site 4, site 1, site 4, site 1. Clearly different performance, right? COP is on the vertical axis, so that one's better. It's higher. We know at least that much, right? And that one's not as, and if you drew a line through this, you'd see, yes, there's a sensitivity to outdoor temperature. The COP goes down when the temperature goes down. So a little bit complicated here, but that's real data. That's how it works in reality. So now a very quick primer on what we're talking about for a ductless mini-split system. We have an outdoor unit, and that outdoor unit has a heat exchanger, and it moves air through it. It takes heat out of the air. It blows the air with a fan through it in that direction. That will be important later. We have a line set that connects the indoor and outdoor unit. We have the indoor unit, and we have return air. That's room temperature air, maybe not, coming into the ductless mini-split, and we have supply air coming out. In this case, we're taking room temperature air, we're heating it, and we're blowing out warmer supply air. So if I wanted to know the coefficient of performance of this machine, what would I have to measure? So for return air, I would have to measure the temperature of the return and the number of CFM, cubic feet per minute of air going through the machine. And then I would have to measure the temperature of the supply coming out, because it's increasing the temperature of the air, right? That's what it's doing. And the same number of cubic feet per minute going in or coming out. And I would have to measure the electricity. That's the input to my black box. So if I take the temperature of the supply air, right, what's coming out, subtract the temperature of the return, let's say this is 90 degrees, let's say the room temperature is 70, that's the difference in temperature, the delta T is 90 minus 70, which is 20. And multiply that by the number of cubic feet per minute of air that are going through this machine, and multiply it by 1.08, which is coefficient of performance, the specific heat of air in cubic feet per minute, I would get the number of BTUs an hour the machine is delivering to the room. Is that clear? Okay. And then if I take that number of BTUs per hour that are coming into the room, and I divide it by this number to change BTUs to kilowatt hours, I'm dividing what comes out of the machine in kilowatt hours by what goes into the machine in kilowatt hours of electricity. That's the COP. Okay, not rocket science here. This is pretty simple. This isn't the perfect model, but it's pretty close. This is good enough. So the line set, right? This connects the two indoor and outdoor unit components. The refrigerant lines are these two things. They're copper, typically flexible tubing, covered in insulation because we're heating them, so we don't want heat to be either gained or lost, depending on what we're doing. We have a little electric wire, and we have a condensate drain. A condensate drain is for the exceptional condition. We're using this in air conditioning. It's dehumidifying. That liquefied water needs to go out of the building. So that's, and so you have these two boxes connected that way. So let's look at a ductless mini-split with a cover off and see what it's about. We have a heat exchanger, right? And a heat exchanger is like a thing that exchanges heat from two different fluids. And this is just like the radiator in your car. We have this copper tubing, right? And we have these aluminum fins very closely spaced together in intimate contact with the copper tubing, which carries, in this case, hot refrigerant. And that hot refrigerant, okay, is used to heat up these fins so the air moves through the fins and it keeps the air. We have these air churning vanes. These air churning vanes do two things. They move the air up and down in a plume, and also move it left to right. So this sweeps the plume of air across the room. And would you believe that the difference in the obstruction of the air impacts the COP? If you turn those vanes all the way to the left and down, you'll get a different COP than having them straight ahead and flat. And that's somewhat important, but useful to know. So then we have that blower pushing air through the machine. So the air is taking from the top and coming out the bottom through the turning vanes. So again, the coefficient of performance calculation, we have airflow. That's important. We have return air temperature, the air coming into the machine. We have refrigerant temperature. So that's important because that's how we're getting the heat from outdoors into the airstream. And then finally, the supply air temperature. If we have more air blowing through this, we can lower the refrigerant temperature. And that means the compressor doesn't have to work as much. And that's a really efficient fan. So blowing more air through this is a very effective way of increasing the COP. So this is a ducted mini split. We saw a ductless machine. This is a little box. It's not very big, as you can see, maybe 8 or 10 inches high, and it's like that big. And so you put it somewhere near the room or rooms you're going to serve with heating and cooling and connect them short ducts. They don't have a lot of pressure, push a lot of air. But they're very electrically efficient because you're not pushing air through massive ducts running through the trunk of a house. You can take this little box, move it near some rooms, and then connect up your refrigerant lines and your electricity and your condensate drain and get the heat close to the room without building big ducts. This is a very nice piece, and one, in my opinion, we should be using more of. So, and then the ducts just go to conventional little vents. We don't like these in this room, and they blow out. So, let's talk about distribution, right? We're making heat in this machine that's sitting outdoors. How do we get it to where we want it to go? This is a 2-story house with 3 bedrooms. We're looking at the second floor, bedrooms 1, 2, and 3. There's a hallway and a bathroom upstairs. How do we condition this? We could put a ductless mini split in each room, like that. Can't really put one in the bathroom. There's no room, right? They're kind of big, you know. Where would you put it? The windows there? Would you put it over the bathtub? No, you can't do that. So the bathroom is really a problem for ductless mini splits. So that is a possibility, right? You leave the door of the bathroom open and hope, or you put a little resistance heating in, that can work. So let's say we have a second floor and we have insulation at the rafters of the roof, not on the attic floor. Now, in the attic floor, we can put ducted system. Now, building code allows you to put ducts above the insulation. I think the building code should really change. It's a great mechanism for making ice dams. It's a great mechanism for wasting a lot of energy because your ducts and things are above the insulation. But this is what we have, and people are doing it right now. But supposing you do go and insulate at the rafters, now you can have your duct system entirely in your conditioned space. It's underneath your insulation. You run some really short ducts to all of these rooms, and yes, you can get heating and cooling into the bathroom as well. It's very easy to do. So this, I think, is a much better solution than the ductless mini split, and something that is should be done more, except people are afraid of ducted designs. John Semmelheck at the FIAS North American Passive House Conference in September presented some really good arguments for why he's doing this for almost everything. He doesn't use ductless mini splits. He's really good at ducted system design. So here's another approach. Just put a ductless mini split in the hallway and this works. It works because we're going to take the case of bedroom 2 and look at it in detail. But it works because we have R34 walls, R55 roof, R5 windows. We have a pretty tight house, and we have, as a negative, we have 28 cubic feet per minute of high-quality supply air going into bedroom 2 that is below the room temperature because no heat recovery ventilator is perfect. It will always deliver air at a lower temperature. So we're going to look at some real data in bedroom 2. And let me explain what this is about. We have a date and time stamp in this column, 1 hour increments. We have the outdoor temperature. And the outdoor temperature starts out at midnight at about 17 and gets down to about 10. And then we have the master bedroom. Now, the important part about this is this door is closed at night. This couple doesn't want their cat in there, so they close the door at night. Doors are left open during the day. Temperature goes from 68.8 down to 66. We've lost 2.5 degrees overnight on the night when the temperature is 10 degrees up. So I think that's pretty interesting. I would call this a success. I actually like my bedroom a little bit cooler than that, but that works pretty well for them. The other interesting thing to note is this is the temperature in the hall, right? And the temperature goes up slightly because this machine is working a little harder because there's heat being lost from other parts of the building. But it's remarkably constant, right? It changes by just about a degree. So this machine, I've got a feeling, I can't tell from this data for sure, but I think it's modulated, which means it's not turning on and off. It's running at exactly the load. I'll show you what that is in a minute.
So that's a high-performance, relatively high-performance home, though, right? You couldn't do this.
R34 walls, yep.
You couldn't do that in a
So this is point source distribution, yes. Now, You would be unhappy in those bedrooms because it would get cold. And if you close the bedroom door, you'd be in the low 50s or below by morning, 40s. Yeah, you would not want to live this way. But with this, these problems go away. You go to Passive House and it gets better. But let's just stick with this for the moment. So this is my model, my mental model. All models are wrong, some are useful, of how a house and heat works. So let's say water in this bucket is heat, and the level of the water in the bucket represents temperature. So in order to keep a constant temperature, we have to pour the amount of water into this bucket that it leaks out at that time. And if we pour exactly that amount in, it will remain a constant level, a constant temperature. If we pour more, the temperature will go up, and the leaks will accelerate. And that's actually true for heat also. And if we pour less in, then our temperature will go down and less will leak out. That's why setbacks work. So the heat leaks from the building and adding heat via the heating system. So Passive House, better than anything else, there are lots of interesting things about Passive House. The philosophy, it's a way of approaching life. But the one thing that it does absolutely the best, particularly in our climate zone, and Graham Wright said this at the Passive House conference, he's the FIAS senior scientist. Passive House crushes space heat demand. If we have a minute after this presentation, I'll show you some buildings with no heating system on that are passive houses, how they behave down to 5 degrees below zero. So if we did that, we would have a very simple problem to solve. We would just use the point source heating. I showed you one per floor and we're done. And it's mainly about cooling. That's why we'd have one per floor. But if we just wipe those out, we have that, but we can't fix the existing buildings. I learned that in deep energy retrofit. We can make some pilot. We can make some incremental improvements. We can't really crush space heating demand without spending a lot of money. So we've got this heat leaking out of the building, and we have to deal with distribution. We have to get heat into these rooms, or they won't be comfortable. So you've heard about inverter drive. What does this inverter drive thing mean? So we have a unit on the outside, and we have our grid. And our grid delivers electricity at 60 cycles per second. And most conventional heating, air conditioning equipment that's made in the US, and maybe some heat pumps too, just operate at 60 cycles. That's what they do and have one output, so many BTUs an hour. Then how do you match the pouring in of the water? How do you match the amount of heat that comes out into the bucket so that it equals the amount of heat that goes out? And the way that's done is by turning the machine on, turning it off, turning it on, and turning it off. And so that heating is delivered in bursts, right, rather than a nice constant level. Inverter drive, and that's the period, the time in the US, it's 1/60th of a second. So inverter drive is different. It changes the frequency. So you change the compressor speed over a pretty wide range, like from your maximum frequency to your minimum frequency. That's a pretty wide range. And the zone of modulation, or the zone in which the machine can change its speed and change the output in BTUs per hour, the maximum and minimum BTUs an hour, is called turn down ratio. And what that means is you might be able to do, let's say, 5 or 7 to 1. In other words, if you're putting out 100 BTUs an hour at minimum and the turn down ratio is 5, at maximum you put out 500 BTUs an hour. Okay? So that's the range that you can adjust and just dial this thing in. Let me show you another graph for turn down ratio. Higher frequencies are less efficient than lower frequencies, just in general, as a generalization. So these are 2 plots of real data from 2 different air source heat pumps. We have power on the vertical axis, and we have time on the horizontal axis. You can see these are on, minutes representing an hour. So the first thing I'd like to draw your attention to is Unit A. So Unit A has turned on, it's consuming power, and it jumps up a little bit, but it very quickly arrives at a stable level. So now it's modulating. It's adjusted its speed. So the amount of water that is pouring into the bucket is exactly equal to what is coming out. And you can see it's hunting a tiny bit there, but it's doing pretty well. And then the next thing that happens is it starts turning on and off, as a conventional system would do. And the reason for that is the amount of heat that is needed to be poured into the bucket is less than its minimum amount of modulation, right? There's a range you can modulate over. It just can't slow down enough. So it's turning on and off and on and off. And that's how it's adjusting the amount of heat that comes out of it. So next, let's look at the red trace. Let's look at unit B. Unit B comes on with a big surge, and it jumps around a little bit, and then it levels off for a short period of time. Then it starts turning on and off wildly, using huge amounts of power, being very, very inefficient. So that happens, and I can show you it's an installation problem, and it's not HVAC. Well, it's an installation problem. We'll talk about that later. All right. So, single split and multi-split. Very quickly, 1-to-1, an outdoor unit, and an indoor unit, multi-split, 1 compressor, and 3 outdoor units. And in this case, we have mix and match. You can connect all sorts of different kinds of ducted, ductless things. So this is dealing with the difference between single and multi-split. The ratio, the turn-down ratio I talked about for single splits, it can be very good. I mean, this is one of the best units on the market that I found. And for multi-splits, it may be less than 2. So we can't adjust, so then we go into that on and off thing. So building heat loss calculation. So how we design to run in the zone. We do a building heat loss calculation using ACA Manual J, how many BTUs are leaking out. We can do that for the whole house or room by room. It's better to do it for room by room. Building code only requires whole house, because room by room is where we want to deliver the heat. Manual S helps you select equipment so it's not oversized or undersized. We have to satisfy the heating and cooling loads, and we want to try to make it run in the zone, so the COP is better. In New Hampshire, Energy Star requires this process to be followed, but not in Massachusetts. This is required for New Hampshire incentives. Massachusetts program dropped this as a requirement. So, according to a Mass Save mailing I got a few weeks ago, only 14% of the homes meet code requirement of designing using Manual J and Manual S in the state. All right, so very quick story. I did a REM rate model for a house I was working on, and I came up with 13,000 BTUs an hour for heating load. The contractor came back with 40. I said, let's look at the inputs. He didn't want to. We got another contractor. He came back with 32. He did work with us on the inputs, and finally we worked them down to a more reasonable number. And this happens all the time. Just because you've got a Manual J in your hand doesn't mean it's right. So, phrases that are used at the bottom of the reports imply something that may not be true. Calculations are approved by ACA to meet all requirements of the Manual J. That means the calculations. It doesn't mean the inputs. The inputs can be wrong, garbage in, garbage out. So Manual S was really created for mix and match technologies. We typically have much higher heating load than air conditioning load. Heat pumps are pretty symmetrical in what they can do for heating and cooling. So this is a problem, and at least Mitsubishi is trying to address this by creating a different design protocol. I'll offer suggestions later. So we're going to get to some real data. This is Rob Aldrich's presentation at the Passive House Conference in Boston this past September. I know Rob from way back. He's a wonderful mechanical engineer, great guy, very knowledgeable, very low-key, and he did one of these studies with measured data. So, on the study he worked on, field performance inverter-driven heat pumps in cold climates, Rob summarized the results of the study as, winter of 2013-14, 10 homes ductless colder than normal winter. The average coefficient performance was 2. Now, what do we need to be better than? Yeah, this is not good news, right? We'd like to see it way better than 2. The range was 1 resistance heating in effect to 2.3. That's kind of interesting. And actually, let me not go into that. So I talked to Rob a lot about the study because they had a lot of trouble measuring the airflow. And remember, measuring that CFM is important to doing that calculation. It's an interesting problem. The second study, mini-split heat pump evaluation, the Cadmus group, okay? And this was done for Mass Save. So Massey has all this data, but it wasn't focused on coefficient of performance. It was focused on claiming savings, because that's their job. So Rob's summary of this study, 100 homes, Duclos, winter of 2014-15, cold, record-breaking snow. Why should that matter? The median COP, so that means half of the 100 were above and half the 100 were below, 1.7. More harm than good. The range was less than 1 to greater than 5, which means there was probably some things going on there that were measurement error or something else. For 2015-16, it was absurdly mild. Now we're at 2.5. So we see what appears to be temperature sensitivity here. And again, the range is all over the map. So this is interesting. Let's go to the next study, field evaluation of advances in energy efficiency in homes for manufactured homes. Rob's summary, low fan speed tripled ductless capacity and efficiency. Remember I told you that fan to that ductless unit is very electrically efficient, meaning that the cubic feet per minute of air it can move per watt of input power is very high, very efficient. So we win by making that fan spin harder, moving more air through the system in the ductless unit, and the compressor doesn't have to work, the outdoor unit doesn't have to work as hard. So that raises the COP. So lowering that indoor unit fan speed really hurts you. And this study claims 60%. I'd like to see a bigger sampling of equipment than this to really make, because I read this study, I read all these studies. High fan speed works. The problem with high fan speed is it blows more air, and if you happen to site the machine incorrectly, it'll blow air on people, and people don't like that. And the other thing is it gets a little noisier. Not terribly noisy, but maybe too much for bedrooms for sure. And we're just talking about moving that air through that heat exchanger. So study number 4, we're going to Vermont. And this is a very interesting study because this one was focused, same Cadmus group study. Cadmus group did the study number 2 where they're focused on saving, and this one where they're focused on COP. Much easier to read and understand. Rob's study, Efficiency of Vermont, is a really interesting organization. They're an independent organization chartered to do efficiency. And they have been doing all sorts of leading edge things like net zero energy mobile home trailers for replacements for all of the homes that were wiped out in floods from Irene. They were doing passive house light buildings. Peter Schneider has got a number of these buildings out there. They're wonderful buildings. So very, very leading edge stuff. The average COP was 3.0. Oh, okay. So it's possible, right? We've demonstrated we can do it in the field. And per the evaluators, this happened because the heat pumps were sized properly. Heat pumps were installed very well, and heat pumps operated very well. So there's a recipe here. I'm going to touch on the 3 items in blue with the slide that follows. So upfront design and sizing, the retrofit market, that's going to be the place where we're going to make a big impact with air source heat pumps for greenhouse gas reduction. So let's look at the real world sales cycle. A friend of mine wants to buy air source heat pumps for his house. He calls some contractors in. They come in, they look at the house, and they give him a quote. No manual J, no manual S, because those things take time. Might take 4 to 6 hours to do an average manual J. And if he's not going to get the job, why does the contractor want to do that? You want to pay the contractor for a bid? Who wants to do that, right? So since there's no enforcement of the requirement, the building code requirement for manual J and S, that doesn't happen. So I wound up doing some calculations for him and going back and forth. We'll see how well it works. You should really think about the application carefully and say, is this a good place for a heat pump or not? And I'll just leave that at that. If you can optimize for high fan speed, we saw that higher indoor unit fan speed makes things better. And a ducted system works too, so you could use ducted systems and make fan speed higher, or in places where a little bit extra noise isn't bad. I mean, it might sound like this. Ductless mini split makes about that much noise, so it's not a big problem for people because we're used to it.
Mike,
yeah.
When you say ducted, do you mean the small duct system?
Like the ones the one I showed in the beginning, yeah. That would be nice because the noise gets away from you. You have less noise than that if you do it right. So the accurate calculations are really important for multi-split. We saw that because that turn down ratio, the sweet spot, that being in the zone is smaller for multi-splits. That's a real problem. And so there may be a better way to do this, and we'll see if we have time to get into that or not. Don't oversize the equipment. When the machines run on and off and on and off, they're very inefficient. That's hard to do in some situations. It's harder to do with multi-splits. So let's think about the future. We're trying to retrofit the 85% of the buildings that are in the ground right now that will be there in 2050. Some people think that if you have an existing gas or oil furnace that you can do this. You can just connect up a ducted mini split. And they have ducted split systems that are large, like Mitsubishi has these, other manufacturers probably do, like existing ones. So theoretically you could do this, but the problem is this. The coil temperature is not as high for an air source heat pump. And it's a big difference, right? So burning oil makes really hot air come out. And so remember I said the BTUs you deliver is the temperature difference, the return air and the supply air temperature difference times the airflow. Well, if you can't make the supply air very hot with an air source heat pump, you have to push more air through it. Most duct systems are undesigned. This is going to fail. You're just going to wind up making people unhappy, running really high fan power. It's not going to work very well. There are some situations in which you can work around some of these problems, but in my opinion, again, building new homes absent a strategy to make them easily fossil fuel free impedes or precludes achieving the greenhouse gas emissions goals. We've got enough problems with the 85% of the buildings that are in the ground in 2050 that exist today. Let's not add to the problem. So, upfront design and sizing. Another thing is that the aesthetics of ductless units are objectionable to some people. They don't want to see that big thing on the wall. If we're going to succeed at targeting a high percentage of the market, then we might want to think about ducted systems, how to do that better and more cleverly. People want to just throw the ductless unit on the wall and get out of it. And everybody likes that, except you may find a lot of resistance in the market. At least that's my mental model. Remember, all models are wrong. That's what I see happening in some situations. Who's doing the quality assurance on the manual J, manual S, right? I just showed you, I was working on my project. I wasn't getting paid to do all that work. There were like 20 or 30 emails back and forth on that manual J to get it down to a point where it was reasonable. Because I had done a calculation in a different piece of software, REMRate, HERS rater software. It's not intended for heating and cooling sizing, but it's pretty close. Every time I've done both, a manual J and a REMRate, they've been within like 20%, a good sanity check. And so who's doing quality assurance on the manual Js and manual Ss that are going to be used to size the equipment now that you understand that they have an impact, sizing has an important impact on performance? That's a question I think that should be answered in a large-scale rollout. Could we substitute a HERS rater calculating or reviewing loads for manual J? That's a possibility. And then somebody follows up on manual S. We could talk about solutions to this problem, but that is a possibility. HERS raters used to do this. They used to look at manual Js. But then the Massachusetts program for new construction incentives dropped that. No more Energy Star. So evaluate all key equipment parameters. NEAT, Northeast Energy Efficiency Partnership, collaborated with a bunch of smart engineers, and they created a spreadsheet, cold climate heat pumps. That's the machine that you want to be using here, not heat pumps that were designed for down south. The extended temperature performance data, 5 degrees Fahrenheit, minus 5 degrees Fahrenheit, minus 13 degrees Fahrenheit, all that data is in the NEAT database if you're interested. So that allows us to design for climates like Great Barrington or even around here. You know, you'd like to know how well the machine is going to perform at lower temperatures. So that data is in that database. There's lots of good information there. Ducted systems can be used to improve indoor air quality. Again, John Semmelhacker gave that presentation about ducted mini-split systems. is putting really high MERV, like 13, 15 filters. You can filter out a fair bit of PM 2.5, and this is circulating in the house, so it's cleaning the air in your house. So that's something else to consider. I have a not completely baked approach to doing a sizing for heat pumps. And I'll just go through this very, very quickly. And it is, do you know what TMY3 is? Typical meteorological year 3. It's a file that has an hour, every hour in the year, 24 hours a day, 365 days a year, 8,760 hours in the year. And it has what a typical January would be for this climate zone, what a typical February would be. Just take real data from different months and they just stick it together. That's your typical climate file. And so in modulation, you know what the heat loss of the building is by the indoor-outdoor temperature difference. So if you take the temperature from this TMY3 scale, the outdoor temperature, and you break it up into bins, minus 10 to 0, all the hours go in there, 0 to 10 degrees, 10 to 20, 10 to 3, make bins, buckets of ranges of data. You can get the manufacturer's performance data of what the COP is in each of those bins. And you can figure out the annual COP, but more importantly is you can figure out the heat loss for those bins. And if you figure out the heat loss, you can tell whether it's going to modulate or not. So without going through this, I think you want to have, these are numbers. This is a turn down ratio, right? That's important. And it varies with temperature also. So that is something that's useful to know. And then that's for single split, and that's a multi-split. Look at how much less turn down ratio the multi-split does. So when we apply those, I think we have to be more careful. And what I've derived here, in essence, is the heat loss of the building identified in one number. And this is the percentage of time, the percentage of hours in the heating season that that it would be in that bin. So you can see most of the hours are here. You don't care too much about this. If this is running inefficiently, so what? It's not even a percent, you know, it's just a percent, a few percent of the year. It's up in this range in Boston, so Boston climate data, where you really care a lot about the COP. Let's not belabor this too much. Let's move on. Okay, so for installation, prefer the gable end. Okay, I'll get to that in a minute. You can put the compressor on a wall to keep it out of the snow, but there's this resonance phenomenon. Some buildings have actually acted like an amplifier for the slight vibration of the machine. Don't put it on the drip line where water is going to fall on it. Don't put it under another unit where its defrost is going to cause water on it. Shield it from the prevailing wind, and the vendors have kit. Be careful about what happens to defrost water so it doesn't clog up or cause other problems. Do not put the return for anything, particularly a ductless mini split, too close to the ceiling. Optimize the height. If you can have things about the same height and line set lengths, you'll save some there. Avoid condensate pumps. Try to pitch the water because that will cause problems if the condensate pump fails. Stop the air conditioner if it works properly. Remote temperature sensor, we can talk about this. When you install the system, the lines have air and moisture in them. You're supposed to evacuate them, test to see if there are leaks, put dry nitrogen in to absorb all the moisture that might be left in there, and purge all that bad stuff out before you put the refrigerant in there because the machine, corrosion will happen and bits will get into the machine and it may ruin the machine. Charging it with the proper amount of refrigerant is very important. These are in the installation guide. You can point to them and say, installer, you have to follow these things. The outdoor unit. So this is in a rather expensive suburb of Boston. There's like a dozen or more zero net energy possible homes, high performance homes. I know the mechanical engineering on his job. He's a really smart guy. He wrote a great spec. It got put out to low bid. So these compressors are on the ground, and when it snows, the owners get to go and shovel it out. Isn't that great? So so this is a little bit better, but this is like central Massachusetts. These stands are not high enough. It's going to drift. This is a little bit better, people, you know, being protected, not really architect design, but It's better protection. This is probably even better. This is a town in Massachusetts. It's about 2,000 feet. It's about 4 feet off the ground. There can be this resonance phenomenon, though. I've actually got a cure for that. I worked with somebody, and we've got little sound dampening rubber mounts. We're experimenting with those right now. Remember that the air goes that way. So, gable end. So that's the gable end of the building, right? And that's where the air source heat pump is located. So there's a sheet metal building in central Massachusetts. Snow slides off sheet metal buildings pretty easily, and that's it. And this is encased in ice, and I walked up on it. Didn't make a dent, right? The person inside didn't even know this had happened. This machine is delivering much less heat. This building is almost a passive house. It really almost doesn't matter how much heat you put into it. Very little heat demand required. So, from one of the studies in 2015, where near historically steep snowfalls buried many units for up to a month. Pay attention to this. You'll have unhappy people. In conventional houses, that person would be very, very unhappy. What do you think did this to the tree? It's October. Notice how it's scorched. That's a prevailing wind. That's a visualization of a prevailing wind. Now, remember I showed you that air source heat pump is trying to blow air out. If you've got a prevailing wind blowing in, you're canceling out the effects of a fan in that outdoor unit. It's trying to move air, and so you're dropping its efficiency. So a shielding kit in a place where there's a prevailing wind is a problem. Savvy operation, that was the third thing that they did right in Vermont. High fan speed. So design the system so that high fan speed is not objectionable. Occupant education on setbacks is important. For most people, I say you set these machines to one speed and you leave them there, one temperature, let them go. Because when they try to catch up, they go into an emergency high speed, high frequency, they run the inverter all the way up, and it's an inefficient way to make heat. So you might think you're making a setback overnight. What's happening is you're using air, the coldest air, first thing in the morning, and you're running the machine at high speed, and it's not efficient. So I'd avoid that. I'd leave it set at one speed for most people. How do you use this with an existing fossil fuel system in case you don't displace the existing fossil fuel system? That is another question to be, and this is in some of the studies. I've got information on that further. Clean and check the air filters. Many people don't even realize these things have an air filter. Anything that has air moving through it probably does have a filter. The controls, understand how they work, use them well, and avoid auto changeover because in a warm day in January it might go into cooling mode because you've got up to 80 degrees. Bad things happen in multifamily. So another few things really quickly. There are 3 machines here. That arrow is pointing in the same machine in both cases. One of them looks frosty, and one of them doesn't, and this is defrost. What happens is you're taking heat out of the air, right, with that heat exchanger. You will start to collect frost. There'll be condensation, and if you're dripping water from the house or something like that, you get a lot of condensation as ice. So in order to get back to that state where there's not a lot of frost, because that's stopping air from getting through the machine, you run hot refrigerant outdoors, right? You blow some heat out there, and it melts, and it drips away. That's defrost. So when that happens, a little wake symbol goes on in your thermostat. Why is that system frosting up? I mean, it was doing a lot. When I was there, it was getting frost on it. Every half hour is going to defrost. It's crazy. Shouldn't be more than 5% of the time. Remember the way the air goes in these machines, right? From the back to the front? I mean, I realize these are the back. So this machine is blowing air that has taken heat out of it into this machine. Now, this machine is getting colder air than air temperature, right? It's getting air that's been pre-cooled by this one. Don't install machines this way. This one wasn't running much, but this one would be getting even colder air, right? So you have to think about what's going on. These things, so many things like this happen. In an assisted living facility with elderly people who don't adapt to technology, would you use the control on the left or the control on the right? Yeah. I have one of these, and I have a little sticker on it to tell me what the sun is and snowflake is, because I forget. So deep setbacks. These people were, this is a recording after I had a lot of complaints about this house. It was point source heating, should have worked. I had complaints, I couldn't speak to the people in the house, so I sent them some data loggers. This one came back, it's in the room with a ductless mini split, and these people were doing all kind of things with the thermostat. So, except for the most sophisticated people, set it at one temperature and forget it, which means you don't get the benefit of setbacks. That's that lower energy button. So I walked into this room and the room temperature felt odd. So I took out my infrared camera and looked around, and I see a pretty serious stratification, right? And I measure it, it's like 72.5 degrees just at waist level, and then 90 degrees at the top. And remember, when you get heat going, when you have return air going in, if it's at a high temperature, that coil temperature has to be at a higher temperature to transfer heat. So this makes the machine more inefficient. How much? Well, if I extrapolate the manufacturer data, I see a COP of 3.31 at 90 and 4.1 at the room temperature. We've lost 19% of our COP because this is stratified. Well, why is it stratified? Didn't I tell you it's like sweeping the vanes back and forth and up and down? Why is the air not mixed? Somebody messed with that complicated remote control on the left, stopped the vanes from moving. So it's blowing out hot air horizontally. Hot air goes, says, oh, I want to go up. And you can see where it stayed up, right? So, the short cycling thing I showed you about, going up and down really wildly, there's power, there's time. That's the one we're going to look at. So they suck this away. Manufacturer's data sheet is not totally clear. They told you some of the things you couldn't do. So what's happening is that air is hitting the bottom of the shelf and going out across the room horizontally. This stratified also really badly. Plus, when it turns on, it blows heat into the little enclosure, and the return is up there, so it self-heats itself. So it's going on and off and not being effective in heating the room and creating stratification, and that's not comfortable either. So here's another case of stratification. The vanes are pointing down. They're hitting this cabinet. At any rate, you've got it stuck up in the cathedral ceiling, so the air like bounces around up here and the heat stays up here. And the same thing happens. The return air temperature is too high. So how do we learn more about the real world? I use the e-monitor that through some of these things. I've got I have thousands of hours of air source heat pump data accessible at 1-minute resolutions to look at and learn from. Check the filters. When you go into a client's home, just pull a filter out and look at it. I do this a lot for ventilation systems. It's really disappointing. And then while you're there, ask them what's happening. You know, what do they think of the machine? How's it going? What do you like? What do you don't like? You learn so much from people like that. I network with other practitioners who are doing the same sorts of things. Investigate client complaints. When somebody complains, figure it out. All sorts of interesting things happen to these machines I haven't described. Again, I'd like to thank Ryan Flynn for his support. Mitsubishi's been great supporting me when I have technical questions. So, here we are here. We're slightly over time. I'll try to get through the rest of this really quickly. Air source heat pumps are much different from the fossil fuel systems we're all used to. Would you agree? I think a lot of this can be overcome by education. But if we don't overcome that, we're going to have resistance, and we're going to have less efficient operation. I think HVAC installers need to have pictures like the ones I have in a guide saying, do this, don't do this, because they don't read all the manuals. They don't know all these things. So that would be something to think about doing. Educate the occupants, particularly the Vermont study. They have occupant interviews information in there that's really telling. The test data and the data sheet doesn't represent real-world operation very well. So maybe we should be looking at the real-world data and learning from that. You could have multi-splits, or you could have a bunch of mini-splits, single splits. And those single splits work really well and reliably. And we've had the houses that were done, one house got done accidentally with single splits. And people said, oh, standby loss is going to kill you. The real world data was actually really good. People are really happy with that house. Hybrid systems, you can have one that has, mini split, a ductless unit here, ducted here, because of different different situations, installation, we really need that protocol for doing better on multi-splits. Quality assurance of load and equipment selection. We need to watch people on that. What is the carbon dioxide equivalent cost per ton of avoided emissions? We need to get that COP up so we can do that now and have it come out better. And what is the curve for that CO2 emissions? We need to realize that we're going to reduce the CO2 emissions per kilowatt of electricity in the grid. Let's project and see where we are so we can see how effective that's going to be. I don't know if I want to get into this other than to say you're giving incentives, same credit for 100% air source heat pump, and if it's PERS rated, or if it's zero net energy ready, or if it's a passive house. This, in my opinion, should be more heavily weighted because it returns more value. Just leave that. All right, so that's that. Do you have any questions?